Sir, you can start now, sir.
Ma'am, can I start the session?
Yes, sir, please.
Okay. Good evening, students.
Good evening, sir.
Yeah.
Good evening, sir.
Yeah. So today we are going to discuss the concept of capacitance. Before that, I will be sharing my whiteboard with you. Are you able to see the whiteboard now?
Yes, sir.
Okay, fine. So today we are going to discuss the concept of capacitance. So actually, you all know very well that whenever you supply a charge Q to any conductor, then the potential of the conductor actually increases. Okay, whenever you supply some charge Q to a conductor, the potential due to the presence of charge actually increases, or there will be a electrostatic potential developing there. So which is because very simple, this is V equal to Q divided by 4 pi epsilon naught into R, where R is the distance between the charge and the point at which the electrostatic potential is calculated. So considering the 4 pi epsilon naught and R as constant, and you have to understand the concept that whenever you supply charge to a particular conductor, then the potential of the conductor actually increases. So whatever charge you are supplying, you are getting a proportionate amount of potential on that conductor. So this Q is actually proportionate to V, and this proportionality 1 by 4 pi epsilon naught R is different. Apart from that, there is a proportionality that the amount of potential generated is actually directly proportional to the charge given to the conductor. So when you replace this proportionality by a constant and you have to put the equal to sign, you have to put C, where C is called the capacitance of the conductor. Okay, it's called the capacitance. So Q equal to CV, so that means C equal to Q divided by V. Okay, so this is called actually capacitance of the conductor. So here we are talking about any isolated conductor, and whenever you supply a charge, you will be getting a potential, and C is actually the ratio of the charge given to the conductor to the potential developed in the conductor. So this is called capacitance, and the capacitance SI unit is actually called farad. Okay, so SI unit of capacitance is actually called farad in SI units, and you have the dimensional formula for this capacitance as well. So the dimensional formula, I am writing it here. So dimensional formula, it is m power minus 1 and L power minus 2 I squared into T power 4. This is the dimensional formula for capacitance. And I have given you the SI unit of the capacitance as well, that is farad, and you have smaller units of capacitance as well. So they are actually microfarad, picofarad, like that. Okay. So you all know very well 1 microfarad is actually equal to 10 power minus 6 farad. Okay. Then another smaller unit is 1 picofarad is equal to 10 power minus 12 farad. So these are the smaller units of capacitance. Okay. So this is the capacitance of an isolated conductor, and now we will be talking about the capacitance of an isolated spherical conductor. Okay. So now I will be discussing capacitance of an isolated spherical conductor. Of an isolated spherical conductor. So for the spherical conductor, let me consider that the radius of that sphere is capital R. So when you have the radius as capital R, the capacitance of the spherical conductor is given by C equal to 4 pi epsilon 0 into capital R. So this is the capacitance of the spherical conductor, and this formula is applicable whenever you place the spherical conductor in vacuum or air. Okay, so that means this capacitance is applicable only when you place the conductor, spherical conductor, in vacuum or air. So here R is the radius of the spherical conductor, and but when you keep that conductor in any other medium, okay, then the capacitance is actually given by capacitance of the conductor in medium, spherical conductor in the medium, it is given by 4 pi epsilon 0 into K into capital R. So here what is the meaning of K? K is nothing but the dielectric constant. Okay, K is nothing but the dielectric constant. So that is equal to capacitance of the conductor in any medium divided by capacitance of the conductor in vacuum. This formula is also applicable for an isolated spherical conductor. You can use this formula as well to find out the dielectric constant. So whenever you want to find out the dielectric constant, you can use this formula also. Capacitance of the conductor in medium divided by capacitance of the conductor in vacuum. And here we have considered the isolated spherical conductor. Okay. So for this, all these equations and formula are applicable. Okay. Right. So actually, how these capacitors are actually represented in numerical problems. Whenever they give you a circuit, the capacitors are actually represented by this symbol. Okay, the two lines are of equal length, or the capacitors will be represented by this symbol. Okay, you are having a line here and you will be having an arc here. So this is how you will be getting the symbols of capacitors, and there are various types depending on the shape and arrangement of the capacitors actually. And actually, whenever you consider a capacitor, it is actually a pair of conductors. Okay, a pair of conductors. So a pair of conductors separated by a dielectric or insulator, or it may even be vacuum. So a pair of conductors is actually called a capacitor. So a pair of conductors separated by some insulator or dielectric or even vacuum is called a capacitor. Insulator or dielectric or even vacuum, it is called capacitor. So there are different types of capacitors like parallel plate capacitor, spherical capacitor, and cylindrical capacitor, depending on the arrangement of the conductors. Okay, right. So now I will be giving you the equation for calculating the capacitance, how you should calculate the capacitance. So as I have already told you, whenever you have two conductors, they're separated by some distance, and the space between the conductors can be filled with insulator, dielectric, or even vacuum. So the pair of conductors means you will be having two conductors here. So this is conductor A, and this can be conductor B. Okay, so this is the pair of conductors, and whenever you want to calculate the capacitance, then C equal to Q divided by potential difference between the two conductors, VAB. Okay, the potential difference between the two conductors, VAB. And whenever you need to find out the VAB, what you should do? So you should actually go for integration. Integration of the dot product of this electric field with dr. So B to A. Okay, the integration limits are from B to A. So this is how you need to find out the capacitance value for a pair of conductors. Q by V is the general formula, and here I am using the integration to find out the potential difference between the two plates. Okay, right. So this is the formula for calculating the capacitance for any capacitor, and now we will be talking about the parallel plate capacitor. Okay, now we will be talking about the parallel plate capacitor. Parallel plate capacitor. What is a parallel plate capacitor? You will be having two parallel metal plates. Okay, you will be having two parallel metal plates. Let me draw them here. So this is one plate, and this is another plate. Okay, and both of these have been separated by a distance d. So here, this distance. Okay, so this distance between the two plates is represented by d. And whenever you give a charge, okay, whenever you give a charge sigma, that is sigma positive, that means you are actually giving positive charge to the plate, to this plate. Okay, so whenever you give positive charge with surface charge density, actually sigma suffix plus. Okay, sigma suffix plus is the surface charge density of the positive charge. whichever you are supplying to this first plate, then second. So here, whenever you give some positive charge to the first plate, it induces equal number of negative charges on the second plate. Okay. So the other end of the plate is actually earthed like this. So here you are having positive charges on one side of the plate, which induces negative charges on the other plate. Okay. So when you have this kind of arrangement, this is called a parallel plate capacitor, and these plates are separated by distance small d, and the area of cross section of these plates, that is represented by capital A. Okay, the area of each plate is represented by capital A. So here the electric field between the two plates is given by E equal to sigma by epsilon 0. Okay, this is the electric field between the two plates at any point. Okay, in the region between the two plates, the electric field value is given by E equal to sigma by epsilon naught, and the capacitance value. The capacitance value of this parallel plate capacitor is given by C equal to epsilon 0 into A divided by B. So this is the equation or the formula for capacitance of a parallel plate capacitor. C equal to epsilon naught A divided by D. Okay, where D is the separation between the two plates. So this is called parallel plate capacitor, and we have discussed the equations for it. So then I will be talking about a cylindrical capacitor. Okay, cylindrical capacitor, and what is the equation for finding the capacitance value of a cylindrical capacitor, that I will be discussing now. So now I will be talking about cylindrical capacitor. So a cylindrical capacitor means you will be having two coaxial cylinders. Okay. So now I will be showing you the coaxial cylinders here. This is one cylinder. So here you will be having that circular section. Okay. So here you will be having this circular section. So then the second cylinder, that is the outer cylinder, is arranged like this. So the outer cylinder is actually arranged like this. So here the inner cylinder radius is taken as small a. So this radius is actually taken as small a. And the radius of the outer cylinder is actually taken as small d. This is the center, and this radius is taken as small d. So now the outer cylinder is actually earthed here. So for this cylindrical capacitor, what is the capacitance value? So that is C equal to 2 pi epsilon naught into L divided by ln A by B. Okay. A is the radius of the inner cylinder and B is the radius of the outer cylinder. So L is actually the length of the cylindrical capacitor. So for finding the capacitance value, you have to apply this formula for a cylindrical capacitor. Okay. So I hope you all can understand these equations. So actually, you all might have studied these equations in your 12th grade. Okay. Actually, since you people are in 12th grade now, you all might have studied all these things. I'm actually recollecting all this information here. Okay. So we have discussed about the cylindrical capacitor and the equation for finding the capacitance here. Now I will be discussing the spherical capacitor. Spherical capacitor. So what is a spherical capacitor? So it is two concentric spheres. So we'll be having two concentric spheres of inner radii A and outer radii B. So let me draw that spherical capacitors here. The outer sphere I will be drawing like this. So the green color one is the outer sphere and the red color one is the inner sphere. So the radius is actually here the radius of this inner sphere is small a. This is small a and the radius of this outer sphere is actually small b. So this is small b and you supply charges to this spherical capacitor with the outer sphere is now here. Okay. The outer sphere is now here and you are supplying charges to this spherical capacitor. Now what is the equation for calculating the capacitance? That is given by C equal to 4 pi epsilon naught AB divided by B minus A. Okay, B minus A. So this is the formula for finding the capacitance value of a spherical capacitor. Okay, so this is the equation or formula to find out the capacitance value for this spherical capacitor. So now I will be giving you a numerical problem. For that, you have to solve the numerical problem and you have to tell me the answer. Okay. So let me give you the problem now. So here is the problem. The capacitance of a metallic sphere will be 1 microfarad if its radius if its radius is nearly, okay, the capacitance of a metallic sphere will be 1 microfarad if its radius is nearly. So I will be giving you the options as well. Option 1, it is 9 kilometer. Option 2, it is 10 meter. Option 3, it is 1.11 meter, and option 4, it is 1.11 centimeter. Now you can solve this problem and tell me the answer. Capacitance of a metallic sphere they have given you, and you know the formula as well. Okay, using the formula you please calculate and then tell me the answer. Students, after completing, you can unmute yourself and you can talk. No issues.
Sir,
Yes, tell me.
sir, can you do the sum, sir? I'm unable to get the answer.
Which formula you have used actually?
Sir, I'm using the formula you just did, sir. Capacitance of a
Yeah, yeah.
spherical capacitor.
So spherical conductor, okay, spherical metallic sphere or spherical thing. So C equal to 4 pi epsilon naught into capital R. You have to use this equation. Okay, so this is 1 microfarad capacitance. That means 1 into 10 power minus 6 is equal to 4 into pi is 3.14 into 8.85 into 10 power minus 12 into r. Okay. So then you have to substitute everything, and r is equal to 1 into 10 power minus 6 divided by 4 into 3.14 into 8.85 into 10 power minus 1. So this is how you need to proceed with the problem. Okay. So now you have to calculate the value in denominator. So then only you will be able to complete the problem. So 4 into 3.14 into 8.85. So what is the value of that? So that will be this is 1 into 10 power minus 6 divided by 111.156. Okay. So 111.156. Now we have to divide this 1 divided by 111.156. What you will be getting, it is, so in the denominator you are having 10 power minus 12 as well. So now the value is 0.0089963. Okay, so 655. This is a bigger value. So this 10 power yes, tell me.
Sir, is the answer 9 kilometers, sir?
Yes, the answer is 9 kilometer. So what you have to do is this 1 by 111.156 is nothing but this value 0.008996365. It's a large value. This 10 power minus 12 you have to take to the numerator. It will be 10 power plus 12, and 10 power plus 12 and minus 6. It will be 10 power 6. Okay. So this larger value into 10 power 6 actually. So when you apply this, what will you get? It will be 8.99 into 10 power 3 meter. Okay. 8.99 can be approximated as 9. Okay. So 9 into 10 power 3, that is 9,000 meter, means it is actually 9 kilometer. So the radius is 9 kilometer. Do you all understand this problem, students? Do you all understand this? Any doubt you have on this?
No, sir, no doubt, sir. Understood, sir.
Okay. Okay. So I hope it is clear till here. Okay. So this is how you need to solve this kind of problem. And now we will be discussing the energy stored in a charged capacitor. Okay. So energy stored in a charged capacitor. And before that, let me ask you, what is the application of capacitors? Do you know anything about that? What is the application of capacitors?
Sir,
Yes, tell me.
sir, it is basically used to store charges, sir.
Yes, very good. So it is the charge storing device actually. Okay, it stores charges and also it stores electrical energy as well. So This is the purpose of capacitors. And can you tell me any one um, place or any one application specifically where the capacitor is used? Can you tell any one application?
So,
Yes.
so in electrical appliances, sir, when the current is being supplied, sir, there'll be capacitor at the point where the appliance is getting charged, sir. Where the
Yes.
current
To
is
be
entering and leaving, sir, so that the voltage and all other, so that the voltage gets it doesn't fluctuate and it's constant, sir, and then the appliance doesn't get affected.
that is actually fuse. Actually, you are trying to talk about the fuse, right? You are trying to talk about the fuse. Actually, I think so. Capacitor is a charge storing device. Actually, it is used. Okay, specifically, I am giving you an example. So, in automobile system for ignition purposes, you need large amount of energy in a short period of time. So, for that purpose, actually, capacitors are used, and condensers are actually one more type of capacitor. So, they are actually used in electrical fans, which we use in our houses. So, that is also one example where capacitors or condensers are used. So, whenever you need some large amount of electrical energy in a short period of time, you actually go for a capacitor. Okay, it was initially people used these capacitors in tube lights. Okay, so now whatever tube lights we are using are having very high power. So the purpose of this capacitors is ruled out now. But actually, when we used tube lights of old type, okay, in that tube lights actually these capacitors were used. So it is actually in the shape of a cylinder. So these cylindrical capacitors were used to provide the ignition to start the tube light. Okay, in earlier times. So when you switch on the tube light, actually the tube light actually flickers for some time, and then the tube light is on. Okay, switched on. But now the tube lights are having high power, so if you switch on the tube light, it goes on instantaneously. But earlier times, we were using a old type of tube light, so there people were using capacitors, okay, for giving the large amount of electrical energy in a short period of time. So that electrical energy is utilized to start the tube light. Okay, so this is one specific application. So actually, since we have discussed now, the capacitor is a charge storing device and it stores electrical energy in form of charges. So now we will be discussing the energy stored. Okay. Energy stored in a charged capacitor. So this thing we will be discussing. So energy stored in a charged capacitor. So a capacitor actually can be charged by connecting it to a power supply. Okay, battery. You can use a battery to charge the capacitor, but it is not easy to bring additional charges into the capacitor because the already existing charges there offers a repulsive force. So what you have to do is you have to supply some, you have to do some additional work, or you have to supply some energy, or you have to do some additional work. Okay, you have to do some additional work to store charges in a capacitor, and that additional work is stored as the potential energy in a capacitor. Okay, so what is the potential energy stored in a capacitor? So we have equation for that, and when the charge in the capacitor is capital Q and the capacitance value of the capacitor is capital C, then the potential energy stored in the capacitor is given by U equal to Q squared by 2C. And this is already equal to half CV square. Okay, this is also equal to half CV square. So this equation is also applicable, and half into Q into V is also a formula for finding the potential energy stored in a capacitor. Okay, potential energy stored in a charged capacitor, we have to use these equations. Okay, so this is how you need to find out the energy stored in a charged capacitor. You will be getting numerical problems of this type as well. Okay, so then we have to discuss the energy density of a charged capacitor. That means energy per unit volume. Okay, so energy density of a charged capacitor. So what is the equation for the energy density of a charged capacitor? So it is represented by the symbol U suffix E. So energy density means energy per unit volume. So half epsilon naught into E squared is the energy density. Energy density is otherwise called energy per unit volume in a charged capacitor. So energy per unit volume. Okay. This is the energy density of a charged capacitor. You can use this equation as well. Okay. So I hope you all understood the concept of energy stored in a charged capacitor and energy density of a charged capacitor. Okay. Now we have to discuss the concept of capacitors in series and capacitors in parallel. Okay, that concept we have to discuss, and before that, I think we can do a numerical problem here. So let me write the problem now. A capacitor of capacity C has charge capital Q and stored energy is W. If the charge is increased to if the charge is increased to 2Q, the stored energy will be the stored energy will be. So this is the question. A capacitor of capacity C has charge Q and the stored energy is W. The charge is increased to 2Q, the stored energy will be. So now I will be writing the options here. Sorry, this is option. This is option 3. Option 3 is 4W. Option 4 is W by 4. So what is the answer for this question? Once you know the answer, you can unmute yourself and then you can talk.
So,
Yes, tell me.
so option 3, sir, 4W.
Yeah, you are right. Can you explain?
So W, sir, it's given that the stored energy is W, sir. We know that the energy is equal to Q square by 2C, sir. So W
Okay.
will be Q square by 2C.
Yes.
And then the charge is then increased to 2Q, sir. So then the new charge taken as U will be 2Q the whole square by 2C, sir, which will give 4Q square by 2C.
Yes. You are
So
right.
and then
Yeah, tell me. Yeah, tell me.
dividing both, sir, you'll get that U is equal to 4W.
Very good. So he is right. But let me explain again to you. Okay. A capacitor of capacity C has charge Q and the stored energy is W. Okay. So they have given you C value, capacitance value, charge value, and energy value. You have to think which equation connects all these things. Okay, the energy stored in a capacitor, you have three equations here. Okay, you have three equations. Now you have to see which equation connects the charge and capacitance here. This is the first equation, Q squared by 2C. So they have given that initially the stored energy is W. Okay, W equal to Q squared by 2C. So initially it is having this much of energy. Now the charge is actually increased to 2Q. That means Q1 equal to 2Q. So now the new energy will be, let me take it as W1. So W1 into Q1 squared by 2C. Okay. So this W1 is nothing but the new energy. It is Q1 means 2Q. So the 2Q whole squared by 2C. That means 4Q squared by 2C. You know very well that Q squared by 2C is nothing but W. So W1 is now equal to 4 into Q squared by 2C. That is nothing but W1 equal to 4 into W. So that means it is 4 times the initial energy that has been given in this option, option 3. Okay, that is 4W. This is the right answer for this question. Do you all understand this problem? Anyone having any doubt?
No, sir.
Yeah, fine. So today we have started the concepts of capacitor, capacitance, and we have discussed the parallel plate capacitor and how to calculate the capacitance of a parallel plate capacitor. So all these things we have discussed today. Okay. So have you all started revising the concept, students? Whatever we have been discussing till now, have you all started revising the concepts? Are you doing regular revision? Students,
Yes,
you
sir.
can, students, you can give your honest reply. Okay. Because why I am asking you this question is for preparing competitive exams, actually you have to do the regular revision. Okay, whatever concepts we teach in the class, you have to revise it regularly. Then only you will be able to get a good command over the concepts. Then only you will be able to solve the numerical problems easily. Okay, so whatever topics we are teaching here, you should do with the regular revision also. Then only this program will be beneficial to you. You can learn many things, and you have to solve numerical problems. Even the example problems given in your NCRT textbooks, you can also solve them too. So no issues. So in that way, you can learn the approach to solve the numerical problems. Okay. So since you will be getting lot of numerical problems in physics part of the paper for this NEET exam. So you have to practice solving numerical problems. Okay, that is very essential. So do the regular revision and try to solve as many numerical problems as possible. Okay, from your NCRT textbooks as well. Okay. So today let's keep it this much for this session, and thank you
Sir,
so much for joining. Yeah, tell me.
sir, I have a doubt, sir.
Yeah, tell me.
Sir, the test paper we did, right, sir?
Yeah, I think I gave you a test for 15 questions actually.
Yes, sir. Sir, that
Ah.
last question, sir, 15th question, sir. Can you do that question, sir?
Right now, I can't do that because it is, we are already running out of time. I think you have to join the next class today. So
Yes, sir.
the 15th question I will be explaining you in our next session. That will be on Thursday. Okay.
Okay, sir.
Thursday when we start the session, I will explain you how to solve that 15th problem. And even if I forget that, you can remind me. Okay, no issues.
Yes, sir.
Okay. Thank you so much for joining the session, students. Do the regular revision, which is very, very essential. Thank you so much.
Thank you, sir.
Yeah.
Thank you, sir.